We're very happy to have Sam to tell us about vertex algebra, the curves and moduli space of sheaves.
Yeah, thank you for the opportunity to speak. I'm going to talk today and Friday, and I think basically the way I'm going to separate it out is that today I'm going to talk about vertex algebras, and on Friday I'm going to talk about curves and moduli spaces of sheaves. So first I'm going to explain kind of the context of what I would like to generalize. Which is W algebras and affine Yangians. So we're going to let M and R be the instanton moduli space. On say 2. And then we'll let just MR be the union over all N of M and R. Hopefully this is familiar to just about everybody, but on the equivariant cohomology of MR, we can construct operators cut product by tautological divisors, and then also Baranowski-Nakajima operators. So cut product is obviously on cohomology, so it keeps the same n. And then these operators depend on some cohomology class. And they go from the cohomology of M and R to the cohomology of M and minus KR. So they go from cohomologies of one space to the other. So these generate an algebra. Beta K gamma. It's an operator defined by convolution, and it basically adds points to sheaves. So we have a rank R sheaf with second term character n, and the correspondence beta is like an extension correspondence where we extend by a skyscraper sheaf supported at a point. But it's really like because we change the instanton number by k, this particular k deletes like k fat points sitting at a particular point. So we take all these operators together. These generate an action of an algebra called the affine Yangian of GL1 on the cohomology of MR for any R. So the first place, and really the main place that vertex algebras show up in this business is that this algebra for a particular R has a huge quotient, a huge kernel. And we might want to ask, what is the kernel of the action, or rather, like, what is the quotient of the algebra that naturally acts on this maybe as an irreducible representation. It turns out that this algebra acts through a completion of the associative algebra of modes of W algebra of GLR. And the action factors through through this quotient. So this is some sort of completion because some expressions require infinite sum stacked in this representation. So I'm going to briefly sort of say I've introduced this object. I'm going to say what it is. And there's kind of a couple of definitions. I'm going to mention some of them. So WK of GLR, which as a particular example of something more general is WK GLR with respect to the action of a particular element. So there's a more general construction that I'll talk about later. In this case is when I omit the element, I mean this particular element has kind of at least three descriptions. One of them is as the cohomology of a complex associated with corresponding affine Lie algebra, tensor with another ghost VOA, modeled on the nilpotent subalgebra of our Lie algebra. And it's the cohomology of this complex with respect to some differential. The differential depends on this E. So here's one definition. It's also a VOA generated by some particular collection of fields. And then for generic values of K, it also has a description as the intersection of the kernel of some operators as beta called the screening operators. The screening operators are particular operators that go from the vacuum module of the Heisenberg subalgebra of our Lie algebra. Again, we're right now in the principal case, to some other modules that depend on the particular choice of beta. The sort of key property of this, other than that it's like intertwiner of representations, is that the commutator of S beta with the zero modes of our Heisenberg algebra is not zero. It's some sort of constant times the same operator. And so the implication is that the action of the zero mode on the source and target are different, which induces sort of shifts of the actions of zero modes.
So my question is, the surjection is why
what is K? This K, so the K is something that depends on H. And the other equivariant parameters here. So in this particular case, I think to match with the like equivariant parameters, it's something like, it depends on what your convention for the central charge is, but it's something like negative T1 over T2 like minus R, or yeah, there's Maybe you're familiar with the notation beta. There's like, I don't know, there's a dozen different ways to write a parameter that keeps track of the like central charge of this Lie algebra, but you can think of it as some complex number, which is related to the deformation parameter of the Yangian. Right. Some particular fields that maybe have like an explicit formula, an explicit and very complicated formula in terms of the Heisenberg subalgebra of the affine algebra.
Did they look like, there's some sort of like a characteristic polynomial of some matrix?
Yeah, you can think of them as like elementary symmetric polynomials in the diagonal fields here. So the Heisenberg subalgebra of GLR is a rank n Heisenberg subalgebra, and these Wi is like the ith elementary. It's kind of the ith elementary symmetric polynomial in those various fields. So it's yeah, we have some sort of relation, which is like if you take like the product over all like tau minus like alpha I of z. Maybe there should be like a derivative here. Then this is equal to like the sum of derivative formal parameter tau, and then the coefficient is like this is to the k like wk, something like this. It's I don't know, some sort of elementary symmetric polynomial in the like Heisenberg subalgebra of GLR. Tau is, so this is the derivative in z, and tau is some sort of formal parameter that's just enters into this formula. And this gives some sort of complicated explicit formula for a set of generating fields for the W algebra. In practice, it's not, I haven't found it that useful because it turns out to be quite complicated. Yeah, tau is just a parameter that, it's like a formal parameter that like enters into just this description. But, if you're more experienced with like instant on moduli spaces, you're going to think of this as like a Verma module for the W algebra. So it's like the, for rank R instant on moduli, as you sum over all n, this is sort of naturally like a highest weight module of the W algebra. Yeah, or yeah, another way to think about it is, yeah, you have the Heisenberg fields, and you don't want them to sort of act independently, but you only want to take the part which is like invariant under the symmetric group that relates them. That literally isn't true, but a natural way of trying to understand that is by taking this expression and saying that this is in some sense elementary symmetric polynomial in those fields. So yeah, and these are kind of related by saying that you can think of a GLR bundle as like a, you know, it maybe has a reduction to the maximal torus of GLR, but you want to take, you know, the while invariance of that maximal torus is something like a GLR bundle. All of these are sort of intuitions that help. The actual formal definition is you have to use maybe one of these slightly more complicated expressions. So there's some sort of story that extends this from instant on moduli spaces on A2 to instant on moduli spaces on other surfaces. So our model is an extension of this story to not any surface, but an AN surface. And our description of our replacement for instant moduli spaces on A2 are going to be Nakajima quiver varieties for an affine type A quiver. This is like affine type n. And then M, yeah, I'll just write it as VW, is Nakajima quiver variety associated to Q. M of W, disjoint union overall V, M of VW. V is now a vector keeping track of the dimension of the quiver. W is our framing vector. And the let's fix some stability condition, and then I'm going to let's take the usual positive one, and I'm going to omit it from the notation for the rest of the talk. So if you care about stability conditions, just take the one with all vectors positive. And the analogous claim to the one above of the affine Yangian of GL1 is that now we have affine Yangian of GLR acts on the equivariant cohomologies of M of W for any W. Right, sorry, that's right, this should be N. Yeah, R is N, yeah, and then R is going to be, no, yeah, so this N is the same as that N, and then R is related to W. So our analog of R is W in this case. Okay, and then we might want to ask the natural question of sort of what is this algebra factor through?
So just to make sure that the nodes of the quiver is labeled from 0 to -1?
0 to n. Sorry, 0 to. But it's sort of an affine. With one node, and it was A0. So here we have n plus 1 nodes, and it's an. So yeah, so we think of it as going from 0, and then here's 1, and there's n. Right. Yeah. Right. So GL1 is 0, so they differ by 1. We might ask what algebra does this action factor through? Right? Again, this is generated by like cut products by Chern classes of various bundles, together with our analog of the Nakajima-Baranovsky operators, are operators EI, FI, and HI generating an affine Lie algebra GLN plus 1 hat. We might ask what this factors through. And I think the exact analog of this statement is maybe not exactly attested in the literature, but there's some sort of, I don't know, like expectation and I don't know, a ton of steps saying what should be the right analog. So yeah, there's, in particular, there's work of Codera and Ueda. And what they do is they construct a map from the affine Yangian of GLN plus 1 hat via its explicit generators and relations to the algebra of modes of a different W algebra, where this is the algebra. Oh, now I'm regretting my decision to put n plus 1 here. For GL. Well, I'm gonna write this as like n plus 1 times the like size of W. And yeah, let's call this like capital N. Which
I'm just saying in the formula, if you write a formula, no, you give you the formula.
you're right. I can yeah, I can ignore this n-1 over here. Yeah, let's yeah, from this vertical line n plus 1. Right, and now we no longer, you know, if I put a parentheses here, this would be a very strange statement. But we now take a different nilpotent element. We're going to take a rectangular nilpotent element. So what is this? We know in GLN that the conjugacy class of a nilpotent element is specified by a partition. And so its conjugacy class corresponds to a partition which is rectangular. And it's going to be, yeah, like n on this side and absolute, the size of W on that side. Well, we're taking like a full decomposition of W into like ones in each factor. And then in the AN case, if you have something supported at a single vertex, all of these are related by the extended affine Weil group that sort of rotates the Nigget diagram. So somehow each, with a 1 here, you know, each, it's just a different representation of the Levi like subalgebra of GLNW. Yeah, I thought for a while about like what happens if right, yeah, the so this kappa is now a central chart is related to
This module could be like some kind of verbal module with some algebra, probably, right?
right, yeah, verbal module for this.
That module, that should be a function of the
Yeah, that's right.
and they all somehow put together in one bucket. They don't keep them kind of in a group of W1, W2.
They I mean no, they're different. We get it like yeah, particular algebra is going to yeah, and the screening operators in the central charge is going to depend on things associated to the various like central charges of like the like Levi subfactors, and yeah, so yeah, in particular the yeah, the screening operators depend directly on the equivariant weights associated to these. But yeah, somehow they all have descriptions in terms of like of this this W algebra. Now, maybe you could ask about like different things if you like I don't know, maybe didn't like fully break the flavor symmetry or like restrict to like a maximal torus. But and I'm also not I'm not making the corresponding claim that the action factors through here. I'm just describing a particular surjection from the like affine Yangian here. Of GL big N, yeah. Yeah, so this is going to correspond to our sort of E rectangular, which is sitting inside some sort of parabolic. In that parabolic, we have our Levi subgroup, which in this case is a direct sum as I goes from 1 up to the size of W of just GL lowercase n. And this algebra similarly has, those three types of descriptions in terms of, a BST reduction, except now our differential is deformed by a character associated to this rectangular E rather than the principal nilpotent E. It's also generated by like matrix valued fields, yeah, I'll mostly just describe its description in terms of like screening operators, because we also know by results of Genra that this is equal to the intersection over all conjugacy classes of roots of GL big N under the action of the Levi of some screening operators associated to those conjugacy classes, the kernels of screening operators associated to these, where yeah, eta is an equivalence class. Roots of GLN, where we, eta 1 minus eta 2 is in the class of 0. Yeah, let's say eta 1 is equivalent to eta 2 of eta 1 plus some root of the Levi is equal to eta 2. And our screening operators just go from a vacuum module where K is now like a vector for the Levi subalgebra to a module that depends on this class. So in a lot of ways, it's exactly analogous to the corresponding Genra. This is a G. So this is the basic context for my talk. I'm going to say something briefly about sort of K-theoretic generalizations of this story. So there are particular operators. So it's a map of vertex operator algebras that in this paper by Genra is given by like an explicit formula from the vacuum module central charge K of the Levi subalgebra of GLN to this module M eta. I didn't define what it is, but it's basically induced from the representation of the Levi on the roots in the conjugacy class eta. So
S is like a map of a VOA?
Yeah, it's a map of VOAs. Or it's it's the 0th Fourier coefficient of a map of VOAs. So it's it comes from a map of VOA, and as vector spaces, it's a map like this.
And the map of the geometry itself, like something like that.
So the diagonal map of like GLN where we
In the n equals 1 case, the Reynolds
yeah, it's like the co-product of all of those. Yeah. And so these precisely these. This is just it's action by the n-fold co-product, exactly. So it's the sum over its action in each of those. So the representation is precisely that. So the rectangular, it's so it's the direct sum of the GLNs along the diagonal. So maybe I'll.
Sounds like the previous story, except everything is now both matrices and finite.
It's roughly a matrix version of the last story. Alpha is just some root for the Levi subalgebra. So there's a subroot system of the root system of big GLN. Yeah, they're equivalent if they're related by some root. So
There's some cartoon picture you can say
it's
This is the concept of the toroidal.
I want to talk about, this is the context for that I'm trying to generalize to Lie algebras other than like lowercase GLN. But you really want to think of this as kind of just like an n by, previously we had GL1 and we're just replacing GL1 by a matrix. So so there's another description. Maybe it'll help to write a description analogous to sort of symmetric functions in the corresponding Cartan, because there's another description of these rectangular Lie algebras due to Arakawa. Gave generating fields for W rectangular. W rectangular, which is this Lie algebra, is generated by fields W, let's see, Wij1 up to Wij size of W. And these satisfy an analogous formula to this. It's just that now the Ij label matrix entries. So Ij go from 1 up to n. And we kind of only symmetrize in the second index. So it really is, as close as possible to thinking of, we're just replacing the like diagonal matrix entries with an n by n block and having everything sort of flavored by an n by n matrix.
So everything just becomes like extra matrices.
Basically, yeah. Right, yeah, the Heisenberg is replaced just by, a matrix analog of the Heisenberg, which is like affine GLN, GL lowercase n. All right, and so, yeah, maybe I'll just say, I'll give some sort of references for a K-theoretic analog. So there's a paper by Nagut on like deformed rectangular W algebras. And here it's actually given a geometric interpretation, but not quite in terms of quiver varieties, but in terms of like their parabolic analogs, so on flags of sheaves. A similar these two papers give sort of related results. This one has lots of authors. Fagan, Jumbo, Mukin. Do a similar result. And the idea is that when we replace our affine Yangian with a quantum toroidal algebra, So toroidal GLR. Then this maps to some sort of deformed W algebra of GL. And this is going to be, R times something which we want to interpret as the size of W, which is the intersection of the kernel of some operators, which are now deformed in some way. So yeah, I just wanted to mention that there's some sort of K-theoretic analog. Yeah, I don't know a K-theoretic analog of what a vertex algebra is, but enough of the structure is like deformable so that we get some sort of like loop analog of this story.
But the instance, I mean, the instance for the structure on like one of the planes.
Right.
That's a very different construction than instance on any surface.
Right, and even even in cohomology, I didn't claim that there's like a geometric like construction of this like map from the affine union of GLR to the modes of the W algebra. Yeah, I just claim that there is such a map, and it's geometric interpretation is not attested in the literature to my knowledge. But hopefully there is one that's quite similar to the case of GL1. So there's also like there's some sort of like technical issue that's in order to construct the representation, so in terms of the state of the literature, it's not actually clear that it's written down somewhere that the Nakajima quiver variety for higher rank for the affine AR is literally isomorphic to like a moduli space of sheaves on the AR surface. But even in the case of just quiver varieties, even if you're like okay with this sort of technical point about moduli spaces, they do the AR surface and they do the like A1 surface, and so the actual AR surface itself is understood, and the rank 1 case is understood. But in terms of like an actual like analog of and if it were a compact surface, there's this like Donaldson-Limbaugh theorem that says stable sheaves are like the same as instantons, but it's not a compact surface, and so it's they were trying to understand this, but it's not quite attested in the literature, the precise isomorphism.
Q is classical thing, I suppose, like quantum enveloping algebra or something like that, or?
Yeah, so it's an analog, except we've replaced our sort of finite dimensional semi-simple Lie algebra with like a toroidal algebra, which is like it's considerably infinite dimensional.
These two loops indicate this abstraction.
Right. They indicate the fact that
What's the other name?
WQT. So there's
WQT. So T replaces
QT together. So together replace this sort of like K and H bar that's
May I ask, what is the K-theoretic aspect of this?
so everywhere you see H, replace it with K.
Okay.
So instead of being equivariant cohomology, it should be the equivariant K theory of these moduli spaces.
So nobody identified with big numbers as a really model.
Yeah, I think this is it's just completely like unattested in the literature, and well, maybe.
No, but the fact that the slide is intertwined, that's kind of enormous.
Right, so it intertwines like these, and then it because of the modular interpretation as a moduli space of quiver varieties, the slice is like a tau map from one quiver variety to the other, and you pull back the universal class, and so it intertwines tautological bundles. So this is somehow like close to a proof. The identification precisely with the say like Genra's screening operators would be what would be necessary to prove precisely this analog. So this is kind of a close to a proof of this statement, is that there yeah, there are these slices, and they do intertwine precisely these actions by, yeah, roughly the argument that I just gave. Okay, so yeah, the stuff that I'm going to talk about, yeah, this has been kind of the context for what's going to be an attempt at a generalization of this story. Yeah, so the goal, and today is going to be entirely representation theoretic, is to extend this story where we've replaced, yeah, according to the following analogy. So we're going to have some sort of surface. We're going to have like an affine Lie algebra, and then we're going to have, I don't know, some sort of W algebra. And when our surface is A2, we have GL1, and we get W algebras of GLR, E principal. When our surface is resolution of A2 mod gamma, precisely these AN surfaces, GLN plus 1, W algebra of GL n plus 1 times the size of W, rectangular. And here we're going to have the cotangent bundle of an elliptic curve. And I'm going to tell you what this like Lie algebra G is. For now, I'm just going to write it as GT star E. Let's tell you what it is. And I'm gonna mostly leave this question unanswered, but I'm going to say something about string operators. Okay. So now I'm gonna actually really answer your question about like what is this object. So this GT star E is going to be closely related to the theory of toroidal Lie algebras. So we're going to let G be a finite dimensional semi-simple Lie algebra. So G is going to be direct sum I in some index set of GI. So somewhat mysteriously, this is an example that nobody ever thinks about in the Cartan classification. So, you know, it's been known for considerably more than 100 years that semi-simple Lie algebras, you know, that are the same as finite dimensional Lie algebras with a symmetric invariant form, and they're classified by an ADE classification. So our sort of main example for today, just a direct sum of semi-simple. This is, yeah, G is a semi-simple Lie algebra. Yeah, the direct sum of simples. Yeah. So our main example is actually going to be like I is equal to the empty set, where G is what we're going to call GL0, which is endomorphisms of exactly. I'm going to explain why it is that this is something that you actually care about. So this is, yeah, so as it's a Lie algebra, it's semi-simple, it's finite dimensional, and it has a symmetric invariant form. It just happens to be like a zero-dimensional Lie algebra.
May I ask, should I run elements here? So, like, if I have a, like, a, like 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 a,
No, it's actually the empty direct sum. So it's the unit for the monoidal structure on vector spaces, which is like a zero-dimensional vector space.
Next time I teach you, I'll start to listen.
So it's not, it's true that the Cartan classification as stated is completely correct. You know, it's like a direct sum of G of A to E type. It's just that it, you know, is the empty direct sum. So there's an important theorem of Castle, which says that, you know, assuming, you know, I is not equal to the empty set, that if we take G of A, so this is, so A is, say, global sections of O on an, for now we can just say an n-dimensional algebraic torus. Right, this is just, you know, maps from variables like S1 plus or minus, S2 plus or minus, up to Sn plus or minus, has a Lie algebra structure. Then this has universal central extension. And our universal central extension is a direct sum of this Lie algebra, one forms on our torus, modulo exact one forms. And this is what we're going to call G hat hat. It's yeah, just our like polynomials in several variables in our semi-simple algebra and then one forms. And right, so now it's going to be clear that we're going to define this even when I isn't equal to the set, is equal to the empty set. So for us, like toroidal GL0 is just one forms modulo exact one forms. This doesn't raise up, does it? This was it's a bad choice of where to put this. So I'm gonna leave this for just 1 sec so everybody can like. C star n, we're only going to, sorry, yeah, this should be, yeah, now we're going to have, I don't know, n hats. But yeah, so we're only going to talk about the n equals 2 case. The theorem actually holds for any n-dimensional central extension. So let's say, yeah, n is equal to 2. And then we're going to say, yeah, a is equal to just variables and 2 variables. And let's just call S1 S and S2 T. But Castle's theorem about it being a universal central extension is true, whatever n is. Yeah, it's actually a very poor choice to write this on this section of board because the next things I'm going to write are like very closely related to the notation that I just put down. But we're gonna have to live with it. I actually kind of think so, yeah. I think the smooth fiber we really want to think of as Cartan type A-1. Yeah, so that's exactly this so it's described as an I0 fiber, but there's a correspondence between Kodaira. This is related to this issue here, which says that the Kodaira IN fiber corresponds to Cartan type A n minus 1. Or Cartan type affine A minus 1. And under this classification, the Kodaira, is Cartan, the smooth elliptic curve is going to correspond to like affine like A minus 1. So there's the Kodaira classification of singular fibers of elliptic fibrations on surfaces. There's a complete classification which has an ADE classification precisely. The theorem goes by saying that curves and surfaces are middle dimensional, and there's a middle dimensional intersection pairing, and then it has to be the elliptic curve itself has to pair to 0 because it moves in a pencil and doesn't intersect itself, and so we get a negative definite intersection pairing on curves, and so it matches pretty much exactly with the Cartan classification. The case of a smooth fiber, under the classification is precisely the corresponds to the like Lie algebra GL0. Okay, so I told you what a toroidal algebra is. Now I'm going to tell you what the full toroidal algebra are and what a toroidal extended affine Lie algebra are. So G toroidal full is this same functions of A. We have one forms on A, modulo exact one forms. And then we also have the space of vector fields on our corresponding torus. And then sitting inside of here, I'll write it as G div. And this is GA. One forms on the torus, modulo exact ones. And then here we're just going to have the kernel of the divergence operator sitting inside of the toroidal algebra. So this full toroidal algebra.
In one dimensional case, that would be the union differentiation.
Yeah. So in the usual case, here we just get so if A is one dimensional, this is our usual story of the affine Lie algebra within a derivation adjoint. And then this is something that really happens for like n is equal to 2 and larger. There's really some sort of slight variation on the story. And then I'll write down the bracket. And the bracket is exactly a higher dimensional analog of the usual story. So the bracket is so that like f of sx, g of sy is equal to bracket of xy, f of s, g of s, plus the term coming from the central extension, which is the pairing of xy times g df, lying in this sort of central part. And then T1 acts by derivations. Say the Lie derivative on functions and also on one forms. So this sort of Right. So this is divergence with respect to the like the logarithmic volume form. So it's yeah. So we're on like flat space, and well, yeah. So I'll explain this divergence free property. It's basically important because it is the requirement that we need in order to get a symmetric invariant form on the corresponding Lie algebra. Well, in the one-dimensional case, the full toroidal algebra has a symmetric invariant form where this has its natural invariant form in the like one vector field and the single central charge paired dually with respect to each other. In this case, there's, on account of the quotient by closed zero forms, we actually only get a pairing that's well defined on this kernel. So GD, it has a symmetric invariant form. Which in particular, when restricted, gives a perfect pairing between exact one forms and divergence free vector fields. Yeah, a non-degenerate symmetric invariant form. Okay, so the main subject of the rest of the talk is going to be a super analog of this story. In Cartan type A-1. So this is going to be based on the cohomology of an elliptic curve. So let E be an elliptic curve. So far, we're actually not using its complex structure. We're actually only taking its cohomology. So you might as well, if you want, replace our elliptic curve with the same 2 torus A. This is sometimes a helpful way to think about it. But what is important is that this algebra, which we'll write an explicit basis for in terms of like an A cycle sigma 1, a B cycle sigma 2, and then a point, which is the cut product of the two of them, is that this is actually a Hopf algebra. So in addition to the like cut product, we also have a natural coproduct, which is given by the pullback along multiplication on the elliptic curve. Yeah, we have a coproduct, which is multiplication pullback. Goes from cohomology of E, cohomology of E times E. And then this operation star, which is the convolution product, is equal to the adjoint of the coproduct. And really what I've done is up to sign, just given you a very fancy way of like writing the cut product on the elliptic curve. So star is conjugate under the homological Fourier-Mackay transform to just the usual cut product up to psi. So the reason I'm writing it this way is going to be clear on Friday, where we give like a geometric interpretation. More geometric than this. We give a geometric interpretation of its use in the algebra that I'm about to define. Yeah?
So you have this, so before you graph this, you cover this pairing in the one form and the vector. Why do you remember that function?
The functions have to be like the inverse of each other, or else it's zero. So it's there's always like yeah. So this pairing is going to be zero unless this one form is like the differential of some function, and that like vector field has the same like poles and divisors as the function we're taking a differential of.
Just making sure that omega A1 is any holomorphic one form
on the two-dimensional torus, yeah. Right. Exactly, yeah. The pairing is zero unless the function and the one form are given, so that there's a basis of these labeled by pairs of integers. So this is isomorphic as a vector space to well, it has a basis given by pairs of integers, so it actually is equal to C, and then particular one forms labeled by a pair of integers A, B. And likewise, yeah, the two components, yeah, and then you can get the other component from one by adding an exact one form. The same is true for like vector fields, so the divergence specifies the like partial s and the partial t components. So this also has a basis in terms of particular vector fields labeled by pairs of integers. And then the pairing is zero unless the vector AB and the vector CD are negative of each other. So it's only, we take, or another way of saying it is we take the usual pairing and then take the like constant coefficient. Right, yeah.
So here is the model like DA0. So only like the dx over x and dy over y. These are like the basis. Otherwise,
Exactly, yeah. Dx.
So it's only not two.
So you have some function times dx over x, unless that function, yeah, so that unless one of A or B is equal to 0, you can get basis elements by like a function like so this k of AB is equal to like s to the a t to the b ds over s, unless but then there's like a one-dimensional subspace, a one-dimensional sublattice where you this is actually exact. So if b is equal to 0, this is exact, and you need to get the basis elements by using dt.
About this guy, why you want to use this way to express that product?
That's going to be clear on Friday. It's mostly to keep track of signs, but also to make the like connection with the geometry like more clear. Okay, and then we're going to define G T star E, which as a vector space is going to be spanned by these elements W, A, B, gamma. So let this basis be capital gamma. There's one other element. There's a central element, which I'll write blackboard bold lowercase c. So A and B are both integers, and gamma runs over a cohomology basis of the cohomology of an elliptic curve. And then we're going to take a bracket which is, it's a super bracket where W gamma 1, AB, W gamma 2, CD is equal to the determinant of the matrix ABCD times W, A plus C, B plus D. Here we're going to take the convolution of gamma 1 with gamma 2, and then we're going to have a central term, which is going to be 0 unless the vectors are the negative of each other. So exactly, parity is exactly parity of gamma. Delta B plus D, 0. There's one number, which is you can just call B, and then you get this sort of central term here. And then B, which is the same B as in WAB gamma 1. You could also say negative D if you want, but there's an asymmetry between the two directions. So if it has, so there's an SL2Z automorphism that acts on this SL2Z, and if you had some sort of linear combination of B and D, you could always pick some SL2Z that makes one of them 0. So there's the central extension is only in one direction, and we're fixing that direction to be the sort of second coordinate of our two vectors in Z squared.
Like you have your synthetic system square, and you choose some algebras.
Yeah, that's probably right. Yeah. It's supersymmetric, so it's just like the coproduct. Exactly. Yeah. The parity is precisely the parity of the cohomology class. Yeah, which that is going to make it clear that because the determinant is antisymmetric, that this is it's like a regular bracket. So it's on a superalgebra. It's like a super bracket, but it's not like an odd super bracket, which has the like insane parity for a Lie algebra. So B is the same B that shows up in WAB gamma 1. So it's that exact same B. So delta forces A plus C to be 0, or else that term is 0. So it's like a delta function. Delta B plus D 0, that's 1 if B plus D equals 0, and it's 0 otherwise. B is the same B, and then C is the basis element of the Lie algebra.
It's extremely confusing. Kind of Blackboard uppercase C that denotes complex numbers and lowercase C which denotes a social extension.
Yeah, I really don't want to do like lowercase c because we also have the lowercase c as an index, and so like, but like mn and kl are used in all sorts of other places. Blackboard lowercase c? No, not really. I think this is basically the only place. You can kind of think of lowercase c as 1 if you want, and you're not going to really lose anything. So yeah, think of Blackboard as a point in the it's a point in the complex plane, which shrinks the capital to a lowercase. But yeah, I'm basically, I don't think I'm ever going to use it again. So one key claim is that this is a Lie algebra. And the reason is that I think, yeah, probably, I don't even actually know if you need the Hopf algebra property, like a Frobenius, I think any Frobenius algebra. So I think any Frobenius algebra is going to give you the structure because it's Hamiltonian vector fields like valued in that Frobenius algebra. Yes, so sorry, what was the question? So cohomology is always a Frobenius algebra, and this is cohomology of a group. Cohomology of a group is always a Hopf algebra. This has both the structure of like a Hopf algebra and a Frobenius algebra. What's really important, basically, for the fact that this works is for it to be a Frobenius algebra. So it needs to have a, I forgot a term. I'm so sorry. There's a, we have to have a pairing of gamma 1 and gamma 2, and then the central term. Yeah, okay, this is why it has to be a Frobenius algebra, is because there's a supersymmetric pairing of the cohomology classes that factors into the central term. Right, and then so this structure, I think is going to be a Lie algebra for gamma with values in any supersymmetric Frobenius algebra. So we have two descriptions. One is it's a central extension of Hamiltonian vector fields on C star 2 with values in the cohomology of the elliptic curve. But the other way to think about it is a central extension of Hamiltonian vector fields on a two-dimensional supertorus. Right, so there's something called like a lowercase, some sort of semi-classical limit of the Yangian is precisely Hamiltonian vector fields on the plane. So somehow there's if we take W1 plus infinity, which is an H bar goes to 0 deformation of the affine Yangian of GL1. This admits like a further semi-classical reduction to something which is called a lowercase W1 plus infinity algebra. And the lowercase w1 plus infinity algebra is exactly Hamiltonian vector fields on C2. So it's like the, so something like the positive half of a Yangian degenerates to Hamiltonian vector fields on C2. So the point, so a sort of key point that I didn't write is that this is Hamiltonian vector fields on C2 with respect to the like usual Poisson bracket. And the Hamiltonian vector fields here are with respect to literally the same Poisson bracket. So with respect to the logarithmic Poisson bracket, which is induced from the usual Poisson form on C2, which we exponentiate the corresponding coordinates to C star 2. On C2, the indices sort of differ. So when we actually take derivatives of the functions, the indices sort of drop down by 1. But when we take Poisson brackets of like exponentials of e to the ax plus by, then the corresponding Poisson bracket is graded in this case rather than filtered. C star squared and what? So the highbrow relation between C star squared and E is that if we take the cotangent bundle of an elliptic curve, then it's twistor deformation. So, and then, yeah, take hyperkähler rotation. We get something which is frequently called C natural, which is not algebraically, but biholomorphically equivalent to C star squared. So the, yeah, C star squared is, yeah, if you're only doing topological things, the exact same thing as the cotangent bundle of an elliptic curve. Or in other words, yeah, so the you could have just as easily replaced the cohomology of the elliptic curve. Yeah, so a consequence of this fact is that the cohomology of the elliptic curve, same as the cohomology of its cotangent bundle, is the same as the cohomology of C star. So as long as you're willing to use the Frobenius structure, which is given by the fact that the elliptic curve itself is compact, then so you hyperkähler rotate from C star, you could have just as easily replaced the cohomology of E here with the cohomology of the same two-dimensional torus. That means it's a super torus. So it's a, we've adjoined to the functions on our two torus, two additional odd variables. Odd variables that, yeah, anti-commute with each other. That more or less exactly correspond to the cohomology classes sigma 1 and sigma 2. It's a trivial bundle, so there's, but presumably there's like a quantum in the same, so there are like quantum tori. So yeah, so there are like quantum supergroups which are non-trivial extensions of an odd supergroup by this supergroup. But yeah, for us, this is just the trivial supertorus. So the UQ, it's not written on the board anymore, but the Q deformation we can think of as like a quantum deformation of this, and it would be interesting to relate this to the supergroup extensions of the odd supergroup by the C star 2. That's, yeah, that's a, I don't know, a supernatural question that I would like to understand, but that's funny. But yeah, for now, this is just the trivial product of a 0 two-dimensional affine superspace with our two-dimensional torus. So the sort of fundamental property is that GT star E has a symmetric invariant form. Which extends the symmetric invariant form on its even part. on G T star E, which has an even part isomorphic to extended affinely algebra of GL0, and then its corresponding odd part corresponding to the odd cohomology classes on the elliptic curve. And it's supersymmetric in the sense that it has the supersymmetric properties exactly as those that are on superalgebras. Great. So most important, in my mind, implication of this fact is that yeah, there's also two even classes in the toroidal extended affinely algebra, right? So that there's those and those. And so the even part here is the even cohomology of the elliptic curve keeps track of the top component and the bottom component. And then the odd is for the corresponding to the odd cohomology classes. And then if you write down the Lie derivative of vector fields on one forms, it exactly coincides with the corresponding bracket here if you restrict to even cohomology classes on the elliptic curve. So G1 is equal to the span of W AB gamma for gamma is equal to sigma 1 or sigma 2, corresponding to the odd generators of the cohomology of the elliptic curve. And then it behaves just like a super bracket in the sense that it, the bracket preserves the parity. We take a bracket of two of those. Cut product or convolution of two odd cohomology classes on an elliptic curve is even. So the bracket of G1 with G1 is in G0. And bracket of 0, 1 is in 1 because the convolution of odd with even is even, and so on. GT star E, so if you take just its bosonic part, so the subalgebra corresponding to even cohomology classes, then this is the exact same thing as G double hat for G is equal to GL0, where we take the divergence-free part, the part that has a symmetric invariant form. Just one at a time, yeah. So the SL2Z action is quite mysterious because it exchanges fields with some horrible things from the language of vertex algebras.
It's not really a four-dimensional field. It's some kind of like a countable connection.
Right, countable connection of two-dimensional fields with an SL2Z automorphism that relates not on the vacuum representation, but the vacuum representation gets under an automorphism gets sent to something where like a field gets sent to some sort of slope diagonal. Yeah, so there's relations so that so somehow if you take like just somehow it controls like solitons and 4D WZW models. So the toroidal algebras are well known to control, and vertex operators constructed from toroidal algebras. So somehow even if you take like an n toroidal algebra, it's kind of closely related to a hierarchy of commuting fields related to like the self-dual sector of four-dimensional Yang-Mills. Or it's better probably to think about it as like a four-dimensional WZW model. So, but at the same time, there's really only, when we construct a vertex algebra structure, we're really sort of specifying, we're singling out one direction. So we're singling out, a structure as a vertex operator algebra. And I'm not going to say anything about constructing like a like a 40 factorization algebra or something on them. It's somehow the way to approach it, I think, is really to single out one direction at a time.
So which one is the B or A or B?
B is going to be the direction over which we sum to keep track of fields in our corresponding 2D story. And then A is just an index. We have a countable integer number of fields in our CFT labeled by A. Great. And then the strange thing is that Fourier transforms on the elliptic curve send fields to things that from VOA language are some like horrible thing. Which nonetheless are fields in the sort of modules that you get by pulling back along the automorphism. I'll hopefully explain some of this stuff. Great. So a key property is that this Lie algebra has a symmetric invariant form, with the implication that there exists a classical R matrix. Let's say R, which is equal to R tilde over some spectral parameter U. It's 1 over U times the sum over alpha, which lives in a pair of integers times cohomology labels of our elliptic curve. And then E minus alpha tensor E alpha, which satisfies the classical Yang-Baxter equation. And then a major problem that I've been working on is to try to like quantize this solution of the classical Yang-Baxter equation. Okay, now I'm going to talk about vertex representations of toroidal Lie algebras. So it was noticed pretty soon after the construction of vertex representations of affine Lie algebras. The lattice construction of the basic representation by Moody, Suara Rao, Yokonuma. That G hat hat, we call this as no vector fields, acts naturally on a particular VOA level 1, which is a lattice VOA associated to this lattice, where we take a hyperbolic lattice, and then we take the finite dimensional Cartan of the corresponding classical Lie algebra. So this sits inside of the actual usual lattice VOA associated to that same lattice, and as a vector space, this is if we label these vectors by U and V, it's labeled by only one direction of the hyperbolic sublattice, and then also the entirety of E lambda for lambda in the root lattice associated to G. Maybe I'll call that RG. Tensor, the Fock module associated to the Heisenberg Lie algebra modeled on, say, the complexification of that lattice. And it became a supernatural question to try to extend this from the Lie algebra with no vector fields to like vector fields or divergence-free vector fields. And this proves to actually be plagued by serious difficulties. Modeled on, so we have a Heisenberg algebra modeled on a vector space, and I wrote the vector space as like L tensor C. So the vector space is just the complexification of the lattice. That lattice, the one, these are both the same lattice. And so it's the dimension of G plus 2 directions.
Can you remind me what spaces are good for implementation? I'm trying to remember.
It's just the, so yeah, so the Fock space associated to some like super vector space with an invariant form, which we think of as like an abelian Lie algebra with a symmetric invariant form. It's just the free module generated by the negative modes. So it's C adjoined like alpha, gamma, minus K, gamma in a basis for H, and K is a natural number.
Is this the space whose L2 functions would use as Hilbert space, or what's the way that is?
This is the Hilbert space of like a free of n free fields where n is the dimension of H. Whether yeah, like you really want to think of these as bosons, except that you can, in the super world, you can have odd bosons that have like that don't obey like spin statistics. So it's yeah, you really want to think of this as the vector space associated to like rank n free boson. It's the Hilbert space of a two-dimensional like quantum field theory of yeah, rank n super boson. Right, so let's recall a sort of basic fact. Actually, it's not basic at all. I don't know how to prove it at all. But that vector fields on, say, the algebra of vector fields on an AB dimensional superspace has a central extension if and only if A is equal to 1. I'm not actually sure about, yeah, so let's take A not 0. I have no idea about the A is equal to 0. So A has to be equal to 1, and B has to be less than or equal to 4. So in the usual case, so these should be invertible. So the usual case of A is equal to 1, we get the Virasoro algebra. And then for adding some extra odd directions, we get you know, the various supersymmetric versions of the Virasoro algebra. But in particular, A is equal to 2 is very bad. So the case that we want, we take, yeah, just vector fields on C2. Yeah, we don't get a central extension of that Lie algebra. Now, on the other hand, there are like worse extensions. So somehow an extension being central is extremely nice and controllable. And what Eswara Rao and Moody did is they constructed an action on that same VOA of an algebra which is vector fields on C star 2, some extension subalgebra, which is an abelian Lie algebra, but admits an action of the corresponding vector field. So if we take such an extension, and we can think of this sitting inside of the universal enveloping algebra of omega 1a modulo d omega 0a, then there is, using vertex algebra formulas, there's an action of this vector fields on C star 2 on these toroidal vertex algebras, V plus 1 of that lattice. Yeah, for a while this was thought of as the best you could do. It's some sort of complicated, horrible abelian extension with some more or less uncontrollable module for the Lie algebra of vector fields. V1 plus L is exactly, yeah, this is L, and it's exactly this like sub VOA of a lattice VOA associated to the Cartan lattice direct sum of hyperbolic lattice. Okay, and then so based on work of Billig, who constructs representations of G double hat full and also divergence free on a tensor product of this V plus 1 of L with some other VOA, which depends on full or divergence free. So while you can't construct it on this, what would naturally be the module you want it to act on, the natural module in which the toroidal algebra acts, if you extend your VOA by taking a tensor product of that VOA with something else, then you naturally get a representation of the full or toroidal extended affine Lie algebras on those VOAs. And then under this interpretation, this vec tilde is just given by vacuum matrix coefficients in one side of operators from here. So it's the coefficient in the vacuum of the action of D in here. So this is D labeled by like a pair of integers, or actually it's some vector field. So let's just take xi. Xi lives inside of vect. If you take its operator here and then take the matrix coefficient of a vacuum, you get some sort of abelian extension of your Lie algebra, which corresponds to the action of this universal enveloping algebra there. So for us, the part of the Fock space corresponding to the odd cohomology of the elliptic curve miraculously cancels this abelian extension. So the theorem is that G T star E acts on a VOA, which is the positive VOA at level 1 associated to the direct sum of a hyperbolic lattice and the Cartan matrix of GL0. Tensor, the vacuum module, I've been calling this, yeah, I'll call it the Fock module based on the odd cohomology of an elliptic curve. Yeah, our Lie algebra naturally acts and it's not a highest weight module, but it acts cyclically in the sense that if you take a single vector, you can create any other vector by the action of this Lie algebra. Right, this is important for geometric representation theory because, you know, if we are just going to take some tensor product with some other VOA, we don't necessarily have a geometric interpretation of it. But by modifying the arguments of Billig to work in our context, we can actually, yeah, construct an action of this Lie algebra here. Maybe I'll say, how much time do I approximately have? I was going to write down like horrible formulas for the actions of generators. That's kind of unclear. But they exist, yeah, via explicit formulas. So I had a guess for what was supposed to be the right thing, and then I like modified it until I made it work using a computer.
And then that's just some sort of direct OP computation.
Exactly, a direct OP computation of certain vertex operators. Yeah, that you yeah, using like Borchard's OP formula and a natural grading on a lattice VOA. So it yeah, it only relies on the like first two like graded directions in the like Fock module part of this VOA, and so you never have to deal with cohomology weighted partitions of size greater than 2. Yeah, there is. So there's an ansatz that gets you kind of close to the right thing. So like maybe I'll explain like not the actual formula, but something kind of yeah, something kind of close. You have to sort of add extra terms to correct. So yeah, ansatz for vertex operators whose modes generate GT star E. So what we're going to do is we're going to construct like an n equals 2 analytic superfield, alpha z theta chi, whose Fourier coefficients in our odd variables are just the free fields associated to the cohomology and elliptic curve. So it's like alpha e of z plus theta alpha sigma 1 of z plus chi alpha sigma 2 of z plus theta chi alpha point of z. And then if you take a field which is gamma a of z theta chi, which is a normal ordered exponential of the antiderivative of this field alpha. And then you would join a correction. Then the Fourier coefficients of gamma alpha are exactly, so it's Fourier coefficients are exactly the generators. Yeah, and I'm not going to write down the correction.
I don't know, but like the question was how much time you have. What if we take another half an hour but insert a break before that? This is something I want to do.
Yeah, I think it's better to somehow summarize what we've said so far. This is the continuation of the topic.
Yeah, I'll talk on Friday and it'll maybe make things make sense.
I think it's better to leave that sort of discussion to after we summarize and make sense of the answer question after that. So that's just
I didn't write exponential. Yeah, a normal ordered exponential of this field. So this actually works exactly right for.
And you say there is a unique that correction is unique?
Right, yeah, it's uniquely specified if you want these commutators to exist. You actually can uniquely specify the correction by just taking commutators with respect to this field. And then once you do this, the Fourier coefficients is A ranges over the integers closed under the informal Lie algebra. And it's precisely this Lie algebra, where we've evaluated the lowercase complex numbers to be equal to 1.
There is no parameter here, which is the analysis
Kappa, yeah, so kind of not yet. So there's some, you can basically get rid of it, but there's also kind of 3 parameters. So yeah, the central charge is a free parameter. The other free parameters are like the actions of zero modes. And then there's also, I've suppressed like an H bar, which shows up that this pairing on the cotangent bundle of an elliptic curve has an H bar here. And then this bracket also contains an H bar. So the bracket is actually like geometrically, naturally, there's for a particular choice of basis of cohomology, this comes with the equivariant parameter scaling the cotangent bundle of an elliptic curve. It kind of disappears if you rescale cohomology classes. Yeah, so in this field, the positive modes have nothing, and the negative modes have 1 over H bar. Is one way to appropriately describe them. Yeah, and then there's kind of there are 3 deformation parameters. One of them is this even deformation parameter H bar, and then there are 2 odd deformation parameters that are kind of the super partners of the usual T1 and T2 from the beginning of the talk.
And is there some sort of statement that this somehow simplifies the
So it simplifies less. So at the values of this specializes when everything becomes trivial when our odd parameters both go to 0. So this, when we have 2 odd parameters that more or less, yeah. So if H bar, it becomes literally trivial. We have, so that. A linear function of the variable. It's kind of a base, so an affine linear function of that variable. Right, yeah, but somehow like literally everything, yeah. It's just so everything except for what's abelian here has kind of has an odd parameter. So wherever we see sigma 1, we can have an odd parameter that, so sigma 1 we kind of replace with 1 odd parameter times sigma 1. Sigma 2 has a second odd parameter that multiplies it, and so the point gets multiplied by the product of these. And these are odd parameters, yeah. Yeah, sigma 1 is odd, and then there's this usual story about superalgebras is that you can replace them with like regularly algebras over a base with odd parameters. So when you do this deformation, our algebra becomes like an even algebra like over a Grossman ring with these variables. Yeah, then we also have this this h bar parameter. And as all three of them go to 0, we actually just literally recover like loops into GL0, 2 loops into GL0, which is a yeah, this G, yeah, this GL, yeah, this is 0-dimensional vector space. Somehow, yeah, so it becomes trivial when all of these parameters go to 0. You can see that even if you, yeah, ignore the odd parameters and just don't do things over this base, but keep this parameter, then the bracket becomes trivial at h bar is equal to 0. So it reduces to like, yeah, a choice of basis reduces to just a completely abelianly algebra at h bar is equal to 0. So yeah, things dramatically simplify when, yeah, any of these parameters go to 0.